Throughout history, humanity has gazed at the heavens with awe and wonder. The night sky, a tapestry of stars, planets, and mystery, has inspired stories, calendars, religions, and revolutions in science. Yet hidden among the beauty lies a sobering truth: space can be dangerous. From the scars on the moon's surface to the extinction of the dinosaurs, there is overwhelming evidence that Earth, and every planet, is vulnerable to asteroid impacts. These cosmic collisions may be rare, but when they occur, their consequences can be catastrophic. A single rock from space, traveling at tens of thousands of kilometers per hour, has the potential to level cities or destabilize global ecosystems. For decades, scientists have warned of this threat, but until recently, the idea of actively defending Earth against an asteroid seemed like science fiction. Could we really stop a space rock hurtling toward us? Could we develop the capability to prevent such a disaster? In 2022, we got an answer, not from theory or simulation, but from a bold, real-world experiment. This was NASA's DART mission, the Double Asteroid Redirection Test, the first full-scale planetary defense test in human history. Its goal: to prove we can change the course of an asteroid. And not only did it succeed, it made history. The DART mission was designed with a simple yet monumental purpose: test whether a spacecraft could nudge an asteroid off its path using nothing more than momentum. No explosives, no lasers, no science fiction force fields. Just a fast-moving object hitting another fast-moving object in space. Launched on November 24, 2021, DART was a low-cost, high-impact mission, quite literally. The spacecraft itself weighed just over 600 kilograms, roughly the mass of a grand piano. It carried no weapons or scientific payloads, just a high-resolution camera called Draco and a sophisticated autonomous navigation system. The target? A near-Earth binary asteroid system known as Didymos and Dimorphos. Didymos, the larger of the two, is about 780 meters wide. Its smaller companion, Dimorphos, orbits it like a tiny moon and measures about 160 meters across, big enough to cause regional devastation if it ever struck Earth, though it posed no actual threat. What made Dimorphos an ideal target was its predictable orbit around Didymos. By impacting Dimorphos and observing changes in its orbit, scientists could measure DART's effect with great precision, like watching a clock and seeing if the second hand starts ticking faster. But hitting a moving target the size of a football stadium 11 million kilometers away isn't easy. It required months of precise navigation, mid-course corrections, and ultimately, total reliance on autonomous systems for the final approach. In its closing minutes, DART had to guide itself in, with no real-time control from Earth due to the communication delay. For 10 months, DART cruised through space, gradually aligning itself with its target. While the spacecraft performed flawlessly, much of the mission's drama centered on those final hours and minutes, a tense countdown to collision. As DART neared Didymos and Dimorphos, its camera, Draco, began sending back images in real time. First, the Didymos system appeared as a faint speck of light. Then, as the seconds ticked down, that speck resolved into two distinct objects. Dimorphos emerged, a small, gray, irregular body tumbling gently through space. In the final 90 seconds, everything was automated. Using its onboard navigation system, DART identified Dimorphos, locked on, and adjusted its trajectory. Scientists and engineers watched from Earth in silence as images streamed in, each one sharper than the last, each one closer to impact. Then, at precisely 23:14 Universal Time coordinated on September 26, 2022, the images stopped. A bright blur, and then black. DART had hit its target dead center, traveling at 22,500 kilometers per hour. It was the end of the spacecraft, but the beginning of something far more important. The mission's success wasn't just about hitting the asteroid, it was about moving it. For weeks after impact, astronomers around the world turned their telescopes toward Didymos and Dimorphos. They measured light curves, observed shadow transits, and used radar imaging to determine any change in the orbit of Dimorphos. Before impact, Dimorphos completed one orbit around Didymos every 11 hours and 55 minutes. After the impact, that period shortened dramatically by 32 minutes. That might not sound like much, but in orbital dynamics, it's a massive shift. It proved definitively that the asteroid's path had been altered, and it was more than expected. Scientists had hoped for a minimum of 73 seconds of orbital change. Instead, the force of the impact, combined with the ejected debris from Dimorphos, which acted like a recoil jet, amplified the deflection. The impact created a plume of dust and rock that stretched thousands of kilometers into space. This wasn't just a fender bender in space. It was an event, visible from Earth and from space telescopes like Hubble and James Webb, both of which captured stunning images of the aftermath. The findings confirmed what many had hoped. Kinetic impact is not just viable, it's effective. A small spacecraft can alter the course of an asteroid with enough force and the right conditions. The DART mission wasn't just a NASA victory. It was a triumph for humanity, a planetary-scale experiment with implications for the entire world. This mission has given us the first tangible evidence that we can defend ourselves from a potential asteroid impact. It's proof that, with the right tools and early warning, we are not helpless in the face of cosmic threats. Planetary defense is now a serious discipline. Space agencies around the globe, from ESA to JAXA to private partnerships, are investing in detection, tracking, and deflection technologies. The goal is simple: identify potentially hazardous objects early enough and give ourselves the time and tools to respond. To build on DART's success, the European Space Agency is preparing Hera, a mission set to launch in 2024. Hera will rendezvous with Didymos and Dimorphos and study the impact site up close. It will map the crater, analyze changes in the asteroid's composition and structure, and refine models for future asteroid deflection missions. This coordinated effort between NASA, ESA, and international scientists marks a new era of space cooperation, not just for exploration, but for preservation. Asteroid impacts may seem like distant possibilities, but they are not just theoretical. Earth gets hit all the time, mostly by small objects that burn up in the atmosphere. But the larger ones, those capable of regional or global destruction, are still out there. There are an estimated 25,000 near-Earth objects larger than 140 meters, and we've only found about 40% of them. NASA's upcoming ENEO Surveyor mission aims to fill in that gap, scanning the sky in infrared to detect faint, dark asteroids that are currently invisible to us. Early detection is everything. The more time we have, the smaller the nudge needed. If we detect a threatening asteroid years or decades in advance, missions like DART could easily push it off course with a gentle impact. But if we wait until it's too close, even our best efforts may fall short. The success of DART gives us a path forward, a strategy that works. But it also underscores the urgency of preparedness. We now have the technology. What we need is global commitment, coordination, and continued investment. The DART mission was, at its core, a message to Earth, to the future, and to the stars. It told us that we are not passive victims of cosmic chance. We are problem solvers, explorers, and protectors of our planet. It marked the first time humanity reached out into space, not to study, not to colonize, but to defend. And in doing so, we crossed a threshold from watchers of the sky to active participants in the solar system.